So when we heard the last presentation, maybe somebody will get some doubts concerning ballastless track, but I would focus on the issue that ballastless track has advantages, and we need also a stabilized subsoil for ballasted tracks as well. So it's not only a special issue for ballastless tracks. This goes. So, yeah. My starting point, nevertheless, is the ballasted track, because the deviation of the development of ballastless track was based on the behavior of the ballasted track. The engineers tried to use the behavior of the ballasted track and transpond it or transfer it to the ballastless track, so that we have nearly the same behavior concerning load distribution. If you look on the ballasted track, this picture is from Dr. Schilder. It's typical Austrian ballasted track with 60 kilogram rails, elastic rail fasteners, concrete sleepers, and the ballast bed. And if you look on the elasticity of such a track, we have about 40% of the elasticity in the ballast and about 60% in the rail fastenings and rail pads. If you want to transform such a system in a ballastless track system, we can use several layers. This is a cross-section out of the new European code, which is just available as a draft. This code gives a very general approach to ballastless track systems and shows the components of such a system in the cross-section. We have the rails, we have the elastic fastening system, or it can also be a continuously embedded rail system. Then we have a precast element, prefabricated element. In regular cases, we can also have some layers not in a special situation. This is a picture showing comprehensive all possible layers. And then we have intermediate layers, boots, for example, or something like that, elastic boots. Then we have a pavement. It can also consist of several layers, such a pavement. And then we have, again, an intermediate layer and the substructure. The load distribution works like this picture shows, also out of this new code. We have the rails, we have the axle loads on the rails, and we have the elasticity here in the rail fasteners, which distributes the heavy axle loads into smaller loads due to the longitudinal distribution of the loads. And then we have also the distribution of the loads into the subsoil shown by this figure, and leading to a pressure on the soil which can be carried without permanent settlements, or nearly no permanent settlements. Different systems use this approach to bring this in practice. So I show you some pictures here. There are the monolithic systems like radar, for example, this here. Then we have also a lot of different systems working with direct fixation on a concrete slab, for example, the Foslo DFF, or also Bandroll is possible. These are the plinth systems, well known also. Then we have the group of the booted sleeper systems, where we have sleepers with an elastic boot, which is put into an in situ concrete. We have continuously embedded rails like the Edelon Cedra system. And then we have the large group of the prefabricated slab systems, where, for example, the Porr slab track system is also one of those systems, and which I want to show you in more detail later on. What are the needs for a ballastless track system? What are the requirements which shall be fulfilled? So different railway companies worked several years on the catalogue of requirements, and this catalogue of requirements depends, of course, on the local situation. For example, we want to have a very general system. Normally, the ÖBB said we want a system which is available, which is usable for high speed as well as high performance. High performance is a special type of track, I would say, with more heavy axle loads, with a mixed traffic. I show later on some pictures about that. The system should be applicable for tunnels, on bridges, and in troughs and on earthwork. Of course, the system should be one system for a whole line and not different systems. The space requirements shall be as small as possible, especially for the application in tunnels, to reduce the cross-section of tunnels, or to increase the clearance profile in old tunnels by installing a ballastless track system instead of a ballasted track system. Then what we want is a high degree of prefabrication. This leads to low work on site and ensures a better track quality, because the quality process can be done in a prefabrication hall where it's better, where it's possible to control it much better. Then what we also want, we want to have low sensitivity concerning different conditions on site. Today we know that most of the systems which exist are good systems, but it depends very much on the local situation on site whether the system is then in practice really a good system or not. If you have, for example, a big sensitivity concerning changes of temperature or something like that, this may lead to a bad track quality finally. And so this shall be avoided as much as possible. Of course, we need low noise and vibration radiation, that's clear. Life expectancy, it was already addressed before. 60 years is a minimum. Now we are going to 80 years and more. What we also need is a great adjustability in height and in position. This is because of the settlements, for example, and moving of the subsoil. What we want is a high alignment quality, the initial alignment quality, because we know that the better the initial alignment quality, the lower the dynamic forces on the system, which leads to a better long-term stability of the system. We need systems which are compatible with all kinds of train control and train protection systems, for example, Ballastless, for example, other systems, inducive, all systems. We need repair options for all elements, because sometimes people say, okay, if you put in a ballastless track, you cannot repair this in a short time, but therefore we need repair options, repair concepts to ensure that all components can be repaired in a short time. Of course, overall cost effectiveness is important, and more countries are also looking at the carbon footprint which a system has when it is installed. So I come now to the Porr slab track system, UEEIV Porr slab track system, which is a joint development of the Austrian Federal Railway Company, UEEIV, and the Porr company. The system is based on a prefabricated element, this so-called elastic layered slab track. This is a slab with a length of about 5 meters and a width of about 2.4 meters. There are 8 pairs of rail fasteners, high elastic rail fasteners on such a slab. And this slab is only reinforced, it's not pre-stressed. And it's installed by underpouring it with concrete. Sometimes this concrete can be reinforced. It does not need to be reinforced when we have a subconstruction which already is reinforced. The system is not connected. The slabs are not connected. The only connection is the rail and the earthing connection, of course. But the slabs are separated each other, so this means that we have the possibility to ensure that temperature changes and creep and shrinkage can move and do not induce cracks. And further on, this makes a repair concept more effective. I show this later on. If you look on the elasticity, when you think about the picture I showed before for the ballasted track, we have a difference because this elastic coating here has only 10% of the total elasticity. It's a rubber granular material, and the largest part of the elasticity is done in the rail fasteners, which is normally the 300 system. If you look at the construction, it's very easy to install the system in a tunnel, for example. We need some reinforcement for the underpour concrete, and the precast slabs are put into position. There are spindle holes on these slabs where we can install the system in the exact position. We are using the final rails normally to put the track into the correct position. You see just here a symbol how to move this system. And afterwards we need only on the side some scaffolding. It's not very much material which is used here. And then self-compacting concrete is filled in. So there is no compacting of the concrete, a special compacting machinery, which this way to install reduces all movements of the track after underpouring it. I was too quick. Back. This is repair concept I want to show. No, I'm too quick. First, some pictures from an installation on site. You see here a picture in a tunnel, installation in a tunnel. Only a few people are necessary on site, so this reduces also the risk of health and safety issues on site. And you see the final track. Repair concept. If you have a derailment, for example, it might occur that the concrete shoulders are damaged. This happened already on several derailments in Austria. Therefore, a repair concept was developed, which consists just of moving away the rail fasteners and the rails and putting in special elements to reconstruct the shoulders. This is with a modified concrete, and afterwards the rail can be installed again with the rail fasteners. So this repair concept was already practiced several times in Austria and worked very well in a short time. So it's possible to repair concrete systems also, not only ballasted track systems. Second problem might be a settlement. In this case, it's possible to exchange the whole slab or to move the whole slab a little bit. Like is shown here, we can open the grouting openings. This was also done in practice, but not for readjusting a settlement. It was just done for exchanging a slab due to some cracks or some such issues which might happen under construction if something was not done properly. You see how this works. You can lift on the whole construction because the separation layer allows very easy to separate the slab from the underpouring concrete, and then it can be filled again and put in. This is a second possibility to correct the position, not using these shims in the rail fasteners, which are very expensive and need a lot of work. If you look on the track quality, this is a protocol from ÖBB where they checked about 700 positions in the track. This is initial track quality. What's shown here is this is a nominal value of zero deviation from the nominal value. This means 0.5 deviation in millimeters plus minus, and this is the percentage of all values which are within this bandwidth. And if you look, for example, for the cant, you can see here that 95% of all measured values are within a bandwidth of -1 and plus 1 millimeter from the nominal value, which shows that it's possible to get a very high initial track quality by ballastless track systems. As we heard before, it's always depending on the situation, which system is the best system or best suited system for the special usage. This is an evaluation for usage of a ballastless track system in a tunnel in Austria. It's just an example. So we identified several aspects, geometric aspects like space requirements in the tunnel, some construction aspects, operational aspects, and additional things which shall be fulfilled. And there several systems were analyzed, and then this solution was chosen to be, in this case, a Porr slab track system. So the first installation of such a system was done in 1989 in Austria in a very difficult situation on an embankment. You see here one track is a ballasted track, and this is the ballastless ÖBB Porr track. This track was already renewed since then, and this is still in the original situation, so it shows that the long-time behavior of such a system is very good. You see also one of the critical elements. This is the transition from ballastless to ballasted track system. To show later on some pictures on that. So we have about more than 25 years experience with the system, and finally I would say the experience is very good. This leads also to a lot of approvals, which the system has already in Europe, starting from ÖBB. Also the EWA in Germany gave approvals for the system. We have also a certificate of network rail, and what's also very important in Europe is the TSI compatibility, which is proven by this certificate. We have now implemented more than 800 kilometers of track with this system. All kinds of track usage are covered by this. We're starting with high performance lines, high speed lines. We have also a system modification for heavy haul lines, where we tested a track in Technical University in Munich, and we have a system for urban and lightweight tracks. So first, high performance lines. High performance lines is typical operational case in Austria, where we run mixed traffic on the same line. We run heavy freight trains and passenger trains with large speeds on the same line. So we have their axle loads up to 25 tons. We have for the freight trains a speed of about 100 kilometers per hour, and for the passenger trains we have speeds of about 250 kilometers per hour. They are all running on the same track. Typical situation on the earthwork in Austria, cross section you see here. We have a load distribution slab which is reinforced, 2 layers of reinforcement. This is a bending element. This allows bending and has a large bending resistance. And on top of this load distribution slab, we install the ballastless track EBB Porr with this underpour concrete and this precast slabs. And the earthwork itself consists of a frost protection layer with a really settlement-free frost protection layer, I would say. You see here a typical example in Austria. This is near Melk, where it was installed the first time on a larger scale on such a line. Other picture out of this installation, you see here the installation phase and here the final system. This system is under operation since the year 2000, and 1 billion gross tons was already operated on this line here without major problems. The most applications we have in Austria are in tunnels, for example in Leinzer tunnel, where we combine the system with floating track slab systems to reduce noise and vibration at the neighbors. This is just an example of such a system. And another one, you see here the heavy reinforced floating track slab system. On the top of this system, the ballastless track EBB Porr is installed. For high-speed lines, we have a little bit another traffic. In Germany, for example, we run axle loads with about 22.5 tons on the VD8 line. The freight lanes have 120 kilometers per hour, and the passenger trains 330 kilometers per hour. German DB developed a special criteria for the track quality which is needed, especially concerning deviations which are showing a certain wavelengths. So the most critical thing for high-speed running is a failure which occurs every, I would say, for example, every 65 centimeters, every 5 meters, which leads to may lead to resonance effects. Therefore, the German DB limits such failures by this power spectral density diagram, which shows how big the deviation is allowed to be, depending on the wavelengths of the deviation. So we did a lot of investigations in this, showing that the typical wavelengths of such a precast system is the length of the slab itself, and of course the distance of the rail fasteners. These are typical wavelengths where systematic failures may occur. And it has to be ensured that these failures are below these limits. This was possible to show, and therefore it was installed in the VDA8 line. You see here a typical cross-section how ballastless track looks in Germany. This is according to German regulations. They use, instead, we have in Austria, we have a bending member, heavily reinforced bending member with 30 centimeter thickness, but only 1 layer. Here in Germany we have 2 layers. We have this hydraulic bonded layer, and on the top we have an 80 centimeter thick reinforced layer, and on this top the elastically supported slabs are installed. A little bit different kind of installation, but with the same effects finally. You see here some pictures also from the installation in Germany. You see it's an embankment, then it goes on a large bridge and it goes in the tunnel further on. So the system needs to be applicable for earthwork, bridges and tunnels. This line is under operation since 1 year now, and as far as I know, it works very well. This is a typical cross-section on the bridge with the same system, the same elastically supported slabs. The only difference is that we need different clips here in the rail fasteners to reduce the tow resistance and to allow the interaction between bridge and track to reduce to allow reduced rail stresses caused by the interaction. Each track shows a lot of special situations. So it's necessary that the ballastless track system can be is applicable on these different situations. For example, as I showed before, floating track slab systems. This is a typical cross section through a heavy mass floating track slab system. The mass is about 10 tons per meter. This was installed in the Lower Inn Valley. This is just a model of the system which was installed there with the ballastless track system on top of the heavy mass. Second special issue is the transition between different systems. It may be a transition between different ballastless track systems or a transition between ballastless and ballasted track system. UEEIV did a lot of investigations on this issue because this was found out as the area where the most maintenance work is necessary on a ballastless track system. It's always in this area here because of the high dynamic impact forces which occur in this area. So therefore, special transition slabs were developed without this elastic coating, which are fixed in the subbase. And we use also auxiliary rails to stiffen the whole situation here. And very important is to use here special rail fasteners to make a very soft, soft transition from the ballasted to the ballastless track system. Other special topic is bridges, especially the joints and bridges. As we heard before, sometimes the bridge engineers don't think about the track on the bridge. Therefore, some bridges show large displacements at the ends, especially if when these bridges are integral bridges, which look very smart, look very good with slender bridges. But the problem is that the track needs to have certain limits of deflections, of movements in the bridge gaps, and therefore we developed a special slab system. This is also the precast Porr slab, but there a special bridge fastening system is mounted on. This fastening system allows higher uplift forces up to 30 kilonewton per rail fastener, and it allows lateral movements about in total 3.5 millimeters, which allows the bridge to move a little bit more than it's in other cases possible. Another special feature is the possibility to go with rubber-wheeled vehicles on the ballastless track system. This may be due to special emergency concepts, for example for tunnels, and therefore we developed this system, which is a system which on one hand allows the cars to move on, but it's also a system which is a kind of guide rail system, because these precast slabs are fixed so that if a derailment occurs, these slabs withdraw this derailment, and the derailed vehicle is guided in this area here. This can also be combined with noise absorbers so that we have a noise absorbing surface and reduce the noise, the airborne noise. Turnouts are a special issue, so we developed this system also for turnouts. You see here cross section through a turnout area. There we use this 300W system for turnouts as a rail fastening system. This needs a lot of special design work because the turnouts are very difficult situations. We have the openings for the point machines and all this equipment on the turnouts, and the positions of the rail fasteners always differ from one slab to another. So there was also developed a special mold which allows to produce such slabs in an economic way. You see some pictures here. This is the installation in Germany, and you see some pictures out of the production. Another problem might be that sometimes we have drainages in the center of the track, and we need openings to clean the drainages. Therefore, large opening constructions were developed to allow the cleaning of the drainage and the access for pumps, for example, and such elements, which can be done very easily due to the fact that these slabs are not pre-stressed, so we have only reinforcement, and therefore it's possible to implement such situations. Yes, if we look on all these aspects, I come now to the conclusion. The system is applicable for high performance and high speed lines. It is applicable for tunnels, bridges, troughs, and on earthworks, and it was already constructed on all these special situations. We have a minimum space requirements. The slab width is 2.4 meters and can be reduced to 2.1 meters if necessary. We have also some installations where we only have the width of the system of 2.1 meters. And the thickness from top of rail to the bottom of the grouting concrete is in minimum 47 centimeters. So this is also a very slender construction. We have a high degree of prefabrication. This is clear because of these precast elements. We have an installation procedure which is not very sensitive according to different situations. It's also because we have low amount of in situ concrete, and we don't use, for example, compacting elements for the concrete. We use this self-compacting concrete. Due to this elastic layer on the bottom of the slab, we have a low vibration and ground-bound noise level as far as possible with such systems. We have a predicted working life of about 80 years. This is out of a study of ÖBB, which was established the last years. They looked on several installations they had and find out that the working life is at least more than 80 years. We have an easy adjustment and repair concept. I showed also that we have a good initial track quality, and we have also compatibility with all kinds of command, control, and signaling systems. So Ballastless can be installed on the top of the slabs, also Indusi and all kinds of other systems. Yeah, life cycle costs are low, and we have a low derailment risk due to this design that that even in case of a derailment, the vehicles are still guided along the rails, especially when we implement these additional elements. We have a large load carrying capacity and a large lateral resistance. We did some tests in Germany where we put on with by jacks horizontal forces on a single slab. We removed the rails and put forces on the single slab, and it was not possible to move the single slab up to loads about, it was I think 1,000 kilonewton for one slab, which is much more than needed. And we have an easy installation of additional equipment due to this fact that it's only a reinforced slab and not pre-stressed, so it's allowed to drill everywhere on the slab for additional installations. And we have accessibility with tired wheeled vehicles. Thank you very much.